Hi, everyone. Thank you for joining our session. In this session, we will give you an update on the MiraclePtr project, the system to mitigate use-after-free attacks. I'm Keishi, and this is Bartek. We're from the Google Tokyo office. Bartek will start by giving you an overview of the system and implementation.
Thanks for the introduction, Keishi, and hello, everybody. Before we get into MiraclePtr and use after free, let me quickly give you an update on what a Chromium Chromium security architecture is. In a nutshell, web content is rendered in a separate process. This process is sandboxed, and that's done so that even if a renderer gets compromised, the damage is hopefully limited to just that process. So, for example, an attacker shouldn't be able to access local files or cookies of another process or start a networking request. However, the strength of this model is as good as the security of the sandbox itself, and the attacker can try to compromise it by either attacking operating system or the browser process that the renderer constantly communicates with. And this could be done, for example, by utilizing a use after free bug in a browser. In short, we're going to call it UaF. And I'm not going to go into details of how this attack exactly could look like, but the slide has an example provided by Project Zero at Google. Well, who doesn't love graphs? So here's one for you that will help you visualize of how big problem UAFs are. In last few years, UAFs constitute about a half of high or critical severity security bugs that impacted Chromium stable. And this graph drills down a little bit further. UAFs is the second bar from the right, and as you can see from the blue rectangle, most of those, actually vast majority of those, come from a browser, which ties back to what I said in 2 slides ago, that an attacker can try to get out of the sandbox using a browser use after free bug, and they have quite a few bugs to choose from. Lastly, this chart shows a breakdown of security bugs that were actually exploited in the wild. And here, UAFs lost their first place, but they're quite high nonetheless. And I would like to emphasize that even if a bug is not exploitable, like we don't really want to assume that because it's hard to prove it 100%. We don't want to second guess ourselves. So if we find a UAF bug in the code, we will fix it right away, and we will merge the fix into the stable release, which, as you can imagine, is not only a huge engineering effort, but also creates a risk on the release, on the product release, which is not ideal. And that's where MiraclePtr comes to the rescue. Before I get into what MiraclePtr is or isn't, let's quickly go over a flow of a UAF attack. An attacker conjectures a dangling pointer, meaning that through their actions they cause Chrome to free memory while there are still pointers pointing to it, and thinking that the memory hasn't been freed yet. Then the attacker, through their actions, causes Chrome to allocate another object in that same location in memory, and this object is filled with data controlled by the attacker. Lastly, the pointer gets dereferenced, and Chrome thinks it's reading the original object while in fact it's reading the attacker's data. No bueno. But the good news is that we have an opportunity to disrupt this flow by simply not releasing the memory as long as there are still pointers pointing to it. And that's what MiraclePtr is about. Here's a high-level architecture of MiraclePtr. The key component is the smart pointer-like wrapper class that we call row_ptr. From the API point of view, it's very similar to what you're used to with unique PTR or say shared PTR. The main difference is that unlike those pointers, row_ptr does not manage the object lifetime, and hence the name. Like we actually called it row ptr specifically so that you treat it the way you would normally treat row pointers t star. From the implementation point of view, row PTR obviously differs from unique PTR and etc. I'm gonna talk more about it in the next slide, but for now I'd like you to know that row PTR relies on the allocator support. And the good news is that Chromium has its own allocator called partition alloc. And even better news is that we recently ran this project called partition alloc everywhere that causes all memory allocations to be intercepted and routed to partition alloc. So we're covered here. Lastly, I want to say that it would be infeasible to convert tons of pointers throughout the Chromium code base from row pointer to row_ptr. And therefore, we wrote the rewriter tool that did it for us. And a few months ago, we ran it and we converted over 15,000 pointer fields in entire Chromium code base. And that's what this process is what we call the big rewrite. And here's the promise algorithm. When an allocation memory allocation request comes to partition alloc, it allocates not only the memory for the object, but also carves out a little bit of extra space for a ref count and puts it right before the object. Row PTR class or object, I should say, whenever it is constructed or assigned a new pointer, it finds the ref count and increments it. Similarly, whenever it's destructed or deassigned the pointer, then it decrements the ref count. Lastly, when a free request comes to partition alloc and it sees that the ref count is greater than 0, it actually doesn't release the memory to the pool and make it available for the allocation. Instead, it quarantines the memory. And it also poisons it by writing trash. Now, I just want to say that the second part, writing trash, is not absolutely necessary for MiraclePtr to work and do its job, but it will help us catch use after freeze whenever Chrome reads some trash, and hopefully a few instructions later it would lead to a crash. We get the crash report and we have an opportunity to debug it. Lastly, when all the row PTR pointers go away, that's when the allocation is actually released back to the pool and available for future allocations. And here I would like to add that MiraclePtr doesn't prevent use after free bugs from happening. We'll continue having bugs in Chromium where free or delete is called prematurely. There's no good way of preventing those, but MiraclePtr disarms those bugs. And we'll still want to fix those bugs with high priority, but the difference is that it could be P1 as opposed to P0 that we have to do now, and we will no longer have to, with MiraclePtr, we'll no longer have to move heaven and earth to merge the fix into the stable channel. We can, do it at our own pace instead. Okay, here let's talk about the scope and focus of MiraclePtr project. So first of all, we're focusing on preventing the exploitation, not so much on detecting UaFs. That's a little bit of an orthogonal problem and a little bit harder to solve. Also, we're focusing on deterministic prevention. We are not so much interested in making exploitation probabilistically harder, because from experience, we know that the attackers will just always find a way to work around this. We're targeting all platforms, and that depends on partition alloc everywhere being available on every platform. And the good news is that it is available almost everywhere. We're only missing iOS support, but the work is in progress. For now, we're targeting non-renderer processes, and the reason is because renderers are performance sensitive, and it may be prohibitive to launch MiraclePtr there, at least without narrowing the scope down very significantly. And also for now, we're focusing on only on fields in classes and structures. We have an ideas how to handle on-stack pointers, but for now, we believe it will be also prohibited from performance point of view. So here, I'd like to use it as a segue to mention that there is no free lunch. MiraclePtr comes at a price tag, and Keishi is going to talk more about this.
I think you are on mute.
Sorry. Next, I will talk about performance. From the get-go, we knew that MiraclePtr will cost us some performance to achieve the amazing security properties. But would it be at an acceptable level? We have been running experiments for over a year to find out. Because of the unique nature of the big rewrite, we had to develop new ways of running the experiments. The full analysis of the experiment results is available in this doc, but I am sorry that this is Google-only data. I will share the rundown of the analysis in percentage numbers here. First, let me talk about the CPU overhead. Most of the CPU overhead is from the ref count manipulation. Raw PTR incurs additional runtime overhead for initialization, destruction, and assignment, as we need to find the ref count and increment or decrement it. However, there is zero overhead when dereferencing a raw PTR. On Windows, there was no change to our guiding metrics except for janky intervals per 30 seconds. On Android, in addition to the janky interval per 30 seconds, we see around 1% regression to first input delay. So there seems to be an impact on jank, but the decision was that the regressions would be acceptable and the impact to the user would be small, especially since MiraclePtr is not adding new long tasks, just making the existing ones a bit longer. Moving on to the memory overhead, let me share the results first. We saw browser process private memory footprint increase around 6-7% on Windows and around 4-5% on Android. MiraclePtr was only enabled for the browser process, and render process does use more memory, but the change was visible for total memory PMF2. So the memory regressions are not small, but we decided the trade-off to be worth it for the security benefit. Also, we did check that the Android OM crash rates did not change. We knew we had three sources of memory overhead. The first is quarantined memory. MiraclePtr quarantines memory referenced by a dangling pointer, meaning it is reserved even after the call to free. The second is fragmentation caused by splitting the main partition alloc partition. Because we have to enable MiraclePtr just for the browser process, we had to prepare a separate partition for allocations before a bit of process initialization. And finally, we have the ref count that is added to each allocation. We needed to know what was causing this regression to see if memory usage can be improved. So we looked into each one to figure out the main cause. Quarantine memory was impossible to predict how much it would be in the real world, so we added a metric to measure it directly. This turned out to account for less than 0.01% change in browser PMF. Next, we looked into the additional fragmentation caused by splitting the main partition alloc partition. This cannot be measured directly, so we created a special experiment group that split the partitions but kept MiraclePtr disabled. The overhead caused by this was less than 1% on Windows and around 1 to 2.5% on Android. So the majority of the overhead must come from ref count added to each allocation, even though we weren't able to measure it directly in the wild. We tried two ways of storing the ref count. Before allocation is the naive solution of having the ref count at the beginning of an allocation. The ref count itself is 4 bytes, but due to alignment, we needed to add 16 bytes to every allocation, and this wastes a lot of memory. Previous slot places the ref count in the padding of the previous slot. Because partition alloc is a bucket-based memory allocator, the allocations often have wasted padding space at the end. This is the difference between the requested size and the bucket size. Previous slot can use that wasted space when available. Only when there isn't enough padding space will we need to use extra memory for MiraclePtr. So very memory efficient. After trying both, we decided to ship previous slot. So we didn't think that the ref count would add this much overhead. Well, it turned out that the distribution of allocation sizes caused more overhead than we expected. Here is a plot of memory used per bucket size. The top chart is when MiraclePtr is disabled, and the bottom chart is when MiraclePtr is enabled. On the x-axis is bucket sizes, on the y-axis is memory usage. The blue bar is requested memory size, and the orange bar is the wasted space due to padding. You can see we have more of that when MiraclePtr is enabled. We identified two causes. First, there are a lot of small allocations where the previous slot optimization doesn't work. Then there are many allocations that have a size of exactly power of 2. When a ref count is added to them, they are bumped up to the next bucket size, wasting lots of memory. So now that we know what is causing the memory overhead, we have interesting ideas for how we can reduce it, but they aren't easy. So our plan is to launch MiraclePtr with performance in its current state. Next, let me talk quickly about how to use raw PTR. For most Chromium developers, the only change they will see during development is that they need to use raw PTR. The rules for using raw PTR is very simple. Please use raw PTR for class and struct fields in place of raw C++ pointers whenever possible, except in render-only code. The details are listed in the usage guideline doc, linked here. Right now, usage of raw PTR is not enforced, but we are developing a Clang plugin that will show compiler errors when raw PTR is not used. Here is an example of what that error might look like. You can always add the raw PTR exclusion macro to opt out of this error. Finally, let me share with you our roadmap. This is what we call MiraclePtr v1. We have implemented backup ref PTR, enabled partition alloc everywhere for most platforms, landed the big rewrite, and evaluated its performance. We have just been approved for launch, and MiraclePtr is getting enabled. We will integrate with ASAN to help with the sheriffing of security bugs, and a Clang plugin will make sure everyone uses raw PTR. This is our roadmap beyond V1. First, we want to increase coverage. We have parts of code like local variables that do not use raw PTR, so we want to support those as well. Also, we are working on technology for debugging and fixing use after free bugs. So that is all we wanted to share with you on MiraclePtr today. Before I go, I'd like to thank everyone that was involved. The two of us are just a small part of the team. The MiraclePtr project is a result of a ton of amazing work from all these people and more from across the globe. So thank you very much.
Thank you.
And
Yes, go ahead.
Yes, I think we have time for questions.
Yes, it's a very interesting project. Thank you for this for sharing that one. Just I had a question. Is it currently logging basically if a section of the memory is poisoned or not? So we can just go through the logs and just find them or something.
You want to?
For example, let's say that I have a pointer that I try to just free, but the MiraclePtr finds out that the reference counter is more than one. So it's already allocated somewhere, but we try to just free that one. Does it log that event somewhere? You mentioned that you are going to just poison that section of the memory with something to make sure that the data is overwritten and it basically contains that section of the memory. But does it log it to a file or something so we can just find a bug for it or something?
So use after free detection isn't part of the scope of MiraclePtr right now. So, but we have, so as I mentioned, we are developing technology to detect and so we can detect and fix those kind of bugs.
Yeah, to add to this answer, we have to be extra careful here because sometimes just having a dangling pointer is not exactly an error. Like there are places in code where memory is freed and the developer knows that it will never be dereferenced after that, but the pointer happens to be dangling for reasons. So we could end up having lots of false positives. But like on the second slide of the roadmap, Keishi mentioned that there is we're working on detection technologies. One of them is dangling pointer detector. And a person working with us, his name is Arthur, he works in Paris. He's currently going through those pointers and trying to figure out which pointers may dangle and which pointers may not dangle. And once we have this annotation, we will actually be able to aggressively detect and crash on unexpected dangling pointers.
Sounds good. The other thing that you mentioned that most of the performance cost is due to allocation of the extra memory. So is there any performance loss because of the data race prevention, like memory fence or something, that when you want to just increment the counter, or right now we assume that everything is done in a single thread?
So are you
have a reference counter in your basically for each section of the memory that is allocated, you're going to have a reference counter to increment or decrement that one. Does it use any atomic basically class?
Yes.
Does it use a memory fence? How you prevent the data race for that one?
We use atomic site. Yeah.
Mhm. And that one, it didn't have any performance costs there, because usually when you use atomic, usually it has some sort of performance cost. Usually it has the CPU, the usage cost associated with it.
I think we need to use it, so we haven't evaluated it. But Bartek, do you
Mhm.
know?
Yes,
I mean,
sure.
yeah, definitely. There is an overhead, and like the overhead that Keishi mentioned, like the junk or what is the other metric? First input delay. Uh, that comes through that from that. We
Mhm.
increase this, CPU overhead ever so slightly on many paths.
Mhm. And if I understood it correctly, if we just use basically that one in the browser, the process, it should be sufficient. We don't need to just implement it in the renders, because the renders they're supposed to be sandboxed. So right now we want to make sure that that sandboxing basically is intact. Yeah.
We want to implement it for the render process as well, but right now, the performance, if we enable it for everything in render process, we know that performance will be not acceptable.
Hmm.
Yep,
That's
we'll have to
correct.
be
Yes.
extra careful with that.
Yeah.
Yeah. Sounds good. And you mentioned that this already is active. So. But the enforcement is not yet.
The enforcement is not
Yeah.
yet, but the protection, Miracle Pointer protection, was just enabled last week.
Okay. Okay. Thank you.
I see some questions from the chat. Could you put reference counts in a separate allocation that has space for a reference count for every space in each bucket? I think the suggestion is to put those kind of
So
like
an
out
out of
out of
line.
line. This idea was on a table at one point of time, I seem to recall, but
Yeah.
I'm not sure why we didn't go for that. I think the problem would be you would just create a more problematic calculation. So we wouldn't be able to quickly find where reference count is, because bucket sizes differ. In which case we would burn more CPU cycles on every row pointer assignment, construction, destruction. Second question is, what happened to the other Miracle Pointer implementations other than backup RefPTR? We went with backup RefPTR just because it has a way to deterministically prevent use after freeze. We consider other approaches. We actually even implemented an MTE like approach. But that was probabilistic. So, in one like of 16,000 cases, like there was like a tag in a pointer would match, and a attacker could go through. Our security team decided that this is not good enough because the attackers have way of generating plenty of uh, cases where this is where we eventually get lucky. Also, we could use side channels as a kind of oracle to find the right tag. So we didn't go with that. There are a bunch of others algorithms on table, but we scratched them out in the design phase. What is the difference between Miracle Pointer and MSFT's MemGc? I'm not familiar with MemGc. Keishi, are you?
No.
Sorry, I won't be able to answer this question. What is the difference between MiraclePtr and shared PTR? Yeah, I guess the difference is that good question. That this in many ways similar. It's got ref counting. The difference is that shared PTR will free the memory for you, whereas MiraclePtr will not. You still have to free your memory, and we can protect you if you do it too early. You might ask a question: why don't we want to convert all the pointers to shared PTR? I don't think it'll be feasible. I think we'll create lots of leaks, particularly if we have like cycles in the objects pointing to each other in a cycle. So you'd have to break the cycle at one point of time, and it would, it's something that you will actually have to put engineering effort to make it right. Whereas with MiraclePtr, we could have just run a tool once to convert 15,000 pointers and call it good. Kantara also says that MemGc is kind of like scan. So it's a different technology. It doesn't require converting pointers to row_ptr. It just scans memory to look for data that looks like pointer and quarantine based on that. So that quarantine part is similar. It's just how you detect what's a pointer is different. Okay, do we have any more questions in the room?
Okay. Right. Yes, so the difference, yeah, so you can free it, but the actual memory isn't freed until all the pointers pointing to it are gone. Is it fair to say that it's like a shared PTR, that it prevents memory from being reused, but it's different that you still have to free the memory, and maybe it doesn't prevent the destructor from being. It doesn't prevent the destructor from being. Yes.
Yes, I think it's a fair statement, David.
Okay, looks like we have no more questions, and yeah, the next session is started. So thanks, everyone.